actuators for robots to grow, age, and decay. This work was led by Yuhan who can't be here for visa reasons, but also done in collaboration with Nathan Scinto-Madonich, Miguel Alfonso Pineros, Pedro Lopes, and Guy Hoffman. All right, so to start, I want to begin with the observation that for typical robotic systems, they're kind of built so that over many years, they'll never change and will always stay the same. We wanted to explore instead, what if robots could grow, age, and decay like living beings? And while growth, age, and decay can be achieved synthetically, none of those artificial methods can really approximate the nuances of how real organisms grow, age, and decay. So we wanted to turn to plants as our method to actually allow robots to grow, age, and decay. Our work builds on and is inspired by a lot of prior work. First, our work builds off prior literature that contests the norms around what a robot should look like. For instance, in Guy Hoffman's The Social Uncanniness of Robotic Companions, he questions why companion robots typically remain in this permanent childlike state. Other research has also envisioned robots that embody more volatile, evolving states, such as incorporating destruction as an interaction. And these illustrative figures also envision plants embedded in robots, which were deeply inspiring for our work. Similarly, our work also draws on prior explorations into developing various robotic mechanisms to allow for robotic movements, different skins and textures, and also shape changing. These approaches all use different materials and mechanical structures to achieve different types of behaviors and interactions. Now note that these are all using electromechanical systems, so DC motors, pneumatics, or shape memory alloys. An emerging line of work has been exploring the unique materiality that comes with designing with living organisms, and some work has also explored this within the domain of plant-robot hybrids. So our approach pulls from all three of these fields of related work, and our work is focused on designing plant-driven actuators for robots to grow, age, and decay. There are many characteristics of plants that really influenced our process of designing these actuators. In many cases, these went against the norms of interaction design. So whereas like traditional interactions are expected to be fast, reversible, on demand, easily expectable, plant-driven interactions depended a lot on the variable and gradual growth of plants, meaning things like slowness, irreversibility, spontaneity, and even potential decay needed to be engaged with. So in our process, we purposefully embrace these more frictionful aspects of designing with plants instead of trying to shy away from them. We thought of plant-driven actuators across 3 layers, the first one being the living layer, then the transmission layer, and then finally the interaction layer. And using the structure of layers, we developed this design space across these layers, accommodating for different states and methods within each layer. In this talk, I'm going to be focusing on presenting 4 of our prototypes. And the first one, we demonstrate how plant growth can be used to induce an increase in the robot's height. So one can imagine height changes representing a robot growing older, for example, kind of mirroring a child's growth. And when we implemented this in our concept with plant-driven actuators across various trials, you'll notice that there's different growth patterns. You might have escape growth, where plants grow outside of the torso cavity, leading to an always short robot, or perhaps the growth is more directed towards the right, causing a tilted head on the robot. So every time that plant sprout grows, the robot's growth is going to be a little bit different, allowing for very surprising, interesting experiences every time. This is a cross-section of how we implemented this, and note that within the robot structure, there are these substructures to allow and accommodate for plant growth. Our prototype uses this simple piston-like structure to gradually expose more and more of the robot's torso and raise its head as the plant growth pushes against the top of its head. We also demonstrate how plant actuation can be used to transform the shape of a robot. You might imagine these shape changes reflecting the robot's feelings, such as feeling more comfortable with the user over time and growing more plump over time. For our prototype, we use silicone structures with walls of variable thickness to induce deformations through plant growth. A soft silicone wall structure allows for plants to push against the walls and expand the shape, allowing for a softening of shape compared to rigid plastic structures. The silicone walls can also be selectively tuned to induce bulging at certain locations, like you can see on the right, where the bulge from growth is concentrated on the top, where the silicone is thinnest. Finally, these silicone cells can also be assembled together, creating, in this instance, a bending across a series of cells. In this third example, we also explored how you could activate joints by designing structures that engage once plant forces have grown to lock them in. So envision a robot that originally has very limited capacity, but slowly over time, it changes to be able to activate more and more joints and achieve more functionality, and perhaps in the end also lose these functions through decay. In our implementation of this, you can see here, initially those top two layers are uncoupled. So that second layer is rotating without transmitting any motion to that top. You can see with the frills, those top frills are not moving, even though that bottom layer is moving. After 7 days, the plants have sprouted into the top chambers, interlocking the two layers, and you can see some of that plant growth peeking out from the side. So after the plants have bonded the two layers together, the joint is activated, enabling a coupled rotation. So now you can see those arms actually being used to propel motion from the servo motor. And this is the cross-section for how we implemented this. Again, with the top and bottom sections initially being uncoupled, but then locked together as plants grow up. Last, in this final example, we also explored how to implement self-destruction by plant-driven means. Now, consider a robot that has agency of its own and can one day refuse to work for you through self-destruction. Here I'm showing a close-up time-lapse of this in action, and notice the time for destruction is different across these two robots, which is dependent on variable plant growth or the strength of connection in the robotic structure. So these structures are designed intentionally with weak joints, allowing plant growth to push against them and destroy them, and allowing the structure to become undone. Depending on those connection types, you can make it easier or harder for that part of the robot to come undone. So in addition to those prototypes, we also conducted an evaluation of those plant-driven actuators by measuring the forces generated by plant growth. So while plant forces have been studied while in soil, they've been less studied in these kind of unique environments that plant-driven actuators would be in. So we felt it was important to conduct these investigations into how these conditions might impact plant growth. We did this by conducting 3 controlled trials of plant growth under different loads and measured the overall displacement of them. And you can see from the graph on the right, generally less load enabled plants to grow taller, but it wasn't necessarily a direct or linear relationship either. There was quite a bit of variability. And we also measured how the plants were impacted by these different load conditions, plotting out differences in stem width and length across conditions. So we see our work as scratching the surface of plant-driven actuation and plant-robot hybrids, and we see a lot of different directions that this work could continue to go in. I'll focus on 3 of those. The first one, we mentioned that these are all new environments and constraints to be studied for plant growth, and 2 additional areas of this are the effect of competition and seed spacing in these enclosed environments, as well as how different growing environments from plastics to hydroponics to soil might impact plant growth. Additionally, future work might also investigate designing actuators to account for more diverse plant types. We focused on small sprouts for our prototyping process, but you can imagine how different types of plants would also allow for really interesting different forms of actuation. And even more interesting would be leveraging diverse root systems and foliage across plants to explore actuation with. Finally, we presented visions of what plant-robot hybrids could look like, but it remains to be studied how the different characteristics afforded by plant-driven actuators could also be acceptable for the social robotics context, and also impact the social behavior towards those social robots. So in summary, we see our work as a start to imagining robots as lifelong companions that can also grow, age, and decay. Our work strove to embrace the unique material properties of plants so that they could inspire us to push on the boundaries of robotic design. We also presented 6 different interaction primitives for future researchers to integrate in their plant-robot hybrids. We really hope that this work can inspire others to similarly entertain the new perspective on designing human-robot interactions, especially things like long-term interactions to elicit empathy and care, introduce unpredictability and irreplaceability, and to not only create robots, but also engage with their destruction and decay. Finally, I just want to give a very special thanks to this extremely interdisciplinary team. We are researchers from HRI, plant biology, and also HCI. So this work could not have been done without all of their perspectives. And also special thanks to Yuhan, who, again, the lead of this work, for bringing this group together. So thank you so much for listening. If you have questions, happy to take them, but also encourage you to reach out to the first author, Yuhan, too.